Hello, thank you for watching our presentation on the autonomous underwater vehicle for the RoboSub Competition, codename Lanturn. We're the Mechanical and Electrical Engineering RoboSub Senior Design Team representing Cal State LA for the year 2021. My name is Christopher, and our team consists of myself, Eddie, Jose, Angel, Yongjie, Louis, Anthony, Daniel, Brian, and Charles. This is our agenda for the day. We will begin by giving background to the competition and objectives and requirements for the project, followed by a system overview. Continuing, we will describe the mechanical and electrical systems in further detail. Then we will describe our work in model simulations before we conclude. I will start us off with the background. The RoboSub competition is held yearly by the nonprofit organization RoboNation and its affiliate sponsors. It is intended to foster the spirit of positive competition and community in STEM, specifically in robots, across a range of age groups and backgrounds. It tasks participants with building an autonomous underwater vehicle, or AUV, which navigates the underwater arena and completes tasks. The image on the right is an aerial view of the arena, the Naval Information Warfare Center Pacific, located in San Diego. During a normal competition year, the AUV will earn points by completing tasks. The smaller images below show examples from last year's competition where the theme was vampires. This, however, is not a normal competition year. Due to the COVID-19 pandemic, the format of the competition has changed, which is why you're watching this pre-recorded presentation. But the AUVs will still be designed with the intent to complete the tasks as if there was a physical competition being held. Scoring will be judged not on AUV performance, but based on a presentation, a report, and a website. Entering into the RoboSub competition this year is Lanturn. Our engineering senior design team has inherited this design from last year's members. Included in our inheritance is the SolidWorks 3D model, rendered images of which are pictured on the right. The top two images are the frame and the hull respectively. The bottom image is a rendering of the two components connected, including the internal components. The project this year, considering the inherited model, consists of three main design steps. But before we even begin, our team first had the task of getting up to speed with what has been done. We distributed the files, analyzed the design intent of the hull, frame, actuated parts, and electrical components. Then we could take the first step and ask the question of each of these components, do they satisfy the requirements? The second design step depends on the answer to the previous question. If the contemporary design did seem to satisfy the requirements, then we move forward and verify the results of analysis that was done and complete any necessary analysis that was not. These could include stress analyses, heat transfer analysis, whatever analysis is required to provide confidence in the performance of the component prior to building and testing. If the contemporary design did not seem to satisfy the requirements, then we move forward and ask the questions, should we modify the design? Should we redesign from scratch? If the design was not finished, should we finish it? Taking into account the scope of the project, in that it is a multi-year, multi-team project, the third step is considering passing the baton, making sure the next year's team is able to get up to speed quickly and as comprehensively as possible, without our team being present to explain anything. This is actually worked on concurrently with the first two steps, and it includes documenting progress, guides explaining how systems worked, and why they were designed the way they were. It also includes documenting problems we encountered or mistakes we made during our tenure so that they would not lose time to similar issues. This step also includes explanations of that which is left to be done. As we present our project, the components will be explained from these three perspectives. What have we inherited? Why would we need to change it? Or how did we verify it needs not be changed? And future work. What problems are we leaving for the next generation to solve?
Hi, my name is Brian Sager, and I'll be going over the objectives and requirements. So the base project objectives were to, as Chris mentioned, to revise the design of the AUV to meet the previous year's RoboSub competition requirements. We did that by identifying the function requirements and then the performance requirements. Our objectives were to then further test and simulate these designs, refine the design, potentially manufacture the sub, and then compete in the competition. But with the new COVID restrictions and in-person requirements, the competition has been moved to being graded on a website, a written report, and a recorded presentation. The high-level requirements that we identified for functional: the AUV shall be submergible, shall house the required electronic systems, be able to navigate autonomously, operate a kill switch, and operate 3 actuated systems, including a claw, a payload system, and a torpedo launcher. Now, specifically, these functional requirements must meet performance requirements. So the submergible AUV must be submergible up to 10 meters and be under 125 pounds. The AUV shall contain a proper waterproofing to house the electronics. The AUV shall receive information from cameras, process that information, and operate thrusters to navigate through waypoints. Operate a mechanical claw to recognize, pick up, and release objects. Operate a payload dropper that will house a payload and release it at a desired location. Operate a torpedo launcher to recognize a target and launch a torpedo and strike it. And the kill switch shall have an optimal way to shut down and be a minimum, and the system shall be a minimum of 0.5% positivity buoyant when shut down through the kill switch.
Next, we move on to the system overview. The 2021 team has inherited designs for frame and hull from the previous year's engineering senior design team. This includes the SolidWorks 3D model. The images on the right are renderings of the inherited model, with only the side handles added this year. The hull and frame are designed to be fully built as separate entities and connected with latches. The hull is cuboidal, which matches the shape of the internal electrical components. This includes the electronic shelving, which is removable and folds open for ease of access of said components. The frame is made of 6061 aluminum with a design allowing for modular attachment of T-slotted parts. More on this in a moment. The 8 thrusters are arranged for ease of directional and translational control. 4 thrusters are oriented vertically, 4 in the horizontal plane at 45-degree angles. The bottom image of Lanturn is a top-down image where forward is indicated by the positive X direction. The black arrow on the right. The 45-degree angles make forward, strafe, and yaw commands all equally simple. More on this in a moment. The T-slotted connection capability of the frame design allows for ease of access and maintenance of all the connected parts, and for quick modification for testing or design alterations. The parts to be attached will first connect to the connection hardware by 4 screws, which are yellow on the top right picture, and the hardware will be attached to the frame by 2 set screws. The functional requirement for our sub is to maintain a minimum of 0.5% positive buoyancy when the AUV is shut down using the kill switch. The properties of Lanturn were found using mass property functions on SolidWorks, which we used on the 3D model. Since we inherited the model, every part needed to be double checked that it had the correct mass. We did so and calculated a 66.5% positive buoyancy for the current design. This high buoyancy presents a problem, but it will be future work for next year's team to address. Because of this, however, buoyancy effects are not analyzed when changes to the design have been made this year. In order to complete tasks, the sub has actuated systems, including a torpedo, dropper, and grabber. The AUV will receive data from sensors for making decisions, including hydrophones, 2 cameras, an inertial measurement unit, or IMU, and a Doppler velocity log, or DVL. Our team will not be discussing the sensors since the computer science portion of our team is taking point on them and they have a separate presentation. Next, we'll move on to the mechanical.
Hello, my name is Angel, and I will be talking about the actuated systems, specifically the dropper, which is one of the 3 actuated systems used for the competition. The dropper system had requirements to be met, which consist of the markers fitting within a box of the following dimensions. 5.1 by 5.1 by 15.2 centimeters. A CAD of the system was made with three major components. These components include the housing, the rotating compartment, and the shaft that connects to the motor. The dropper system will attach to the shaft of a servo motor to rotate and release the markers. It will have to be 3D printed.
Hello, my name is Anthony, and I will be discussing the claw/grabber portion of the project. When it came to the grabber, last year's team left us with two placeholder designs. Both designs had no mobility capability or any testing done. The first design was created by the team but seemed to have been a step file, so the parts were unable to move. The second design was a grabber sold by Blue Robotics. Although due to this design no longer being sold, and with no info or timeline for when the revised design will come out, our team had no choice but to build a grabber design from scratch. When researching grabber designs of previous winning teams as references, focus was placed on their placement on the grabber in relation to our own, and how well the team performed in the grabber challenges of the competition. With this in mind, the design on the right was made. The grabber design uses a combination of 3D printed parts and aluminum materials. The white components of the model represent 3D parts, while the gray components are aluminum. The arm is made with two parallel aluminum sheets, which are connected by aluminum linkages and tightened with hex nuts. A servo horn will be connected to the gears of the motor to have a larger surface area to better distribute the pressure created when moving the claw and/or arm. Furthermore, the servo horn functions as a way to connect the arm and claw to the motor at multiple points for better support and motion. The design will be equipped with two HS646 servo motors due to the motor being IP67 rated and routinely used by many teams. And here we can see the grabber model in motion on SolidWorks. The grabber will be mounted at the bottom of the sub using the T-slot frame last year's team designed for mounting the actuator systems and other components. The placement of the grabber remained unchanged from last year's, as the claw needs to be in view of the camera for the sub to make real-time adjustments during the competition. The mounting system will be connected to the sub using set screws like the other components. Stress tests were performed on the claw to determine how the motion will impact the durability of the claw when performing the task of grabbing objects. Using the objects of 2019's competition as they were the most recent models, as 2020 and 2021 were virtual. The first object was a crucifix prop, which had a factor of safety of 3.3, whereas the second object was a garlic prop with a factor of safety of 1.7. In both cases, the point of highest stress was located at the holes where the blue mini grippers connect to the claw. When designing the claw, we had these objects in mind, as historically the objects in this challenge are cylindrical objects and have a diameter of approximately 1 inch. For the waterproofing of the servo motors, we decided to go away from designing and building a bulky waterproof enclosure and looking at less intrusive methods. This led to the use of applying mineral oil to the inside and outside of the motor and sealing the seams with epoxy, as the image shows the servo being coated in mineral oil. This solution allowed our test servo to run for an hour under shallow water. Additionally, this method was tested by a separate team with their servo motor being submerged in seawater between 14.8 feet to 22 feet in depth, which is approximately 4.5 to 6.7 meters. The servo used by this team was a cheap 9-gram servo and functioned well under these conditions. Using our testing and separate testings, we are confident that our servos will have no issues operating for the 15 minutes and the max depth of 5 meters for the competition using this method.
Hi, my name is Yongjie Lee. I will be talking about Torpedo of the actuator system. Last year's team didn't give us any design for the torpedo launcher. There was just one placeholder. It was supposed to be the the gas compression system, but now this year I have started from new because that was just a placeholder. This year's design will be using a spring compression system. This system consists of 2 stainless steel compression spring, a 3D printed housing, and a HS5086 WP waterproof servo, and it will be a sheet metal gate system locking the torpedo in place. Inside the torpedo there will be a aluminum rod holding everything in place, holding the compressed spring and the torpedo from going random direction. Next. The placement of the torpedo launcher the torpedo launcher will be mounted with screw and bolt, and the placement will be the same thing where last year's was meant to place. It's supposed to be placed on the bottom right side next to the camera, so it will have a clear view of our target, and it's like close to the camera, so we have easier to calculate the offset. The torpedo design have field requirement from the competition. First is the size. It's supposed to be the same size as the dropper. And the size limit is 5.1 times 5.1 centimeter and 15 centimeter long. The weight it should be no less than nothing more than 2 pounds, and it should be marked with the team's logo on it. And this next slide. The torpedo design this year had 3 different iterations. The first one was from the Team Arctos. It was a prototype that I get inspired from, but it turned out it doesn't fit our design because the gate, our gate is more in the front compared to the one that they have, so I can't use their design. So the second design, it was the new one that I designed, and it have poor fitting, and it didn't fit my design that well. The last one have and they also have a small fin area. The last version is based off of real torpedo and have the max fin area compared to all the other design. Here I did fluid simulation based on the torpedo to my final iteration of torpedo. The goal of the torpedo, the goal is to get drag coefficient to 0.2, but I ended up getting drag coefficient of 0.33. So I could use it to find trajectory in the water. For this equation, we'll need the input of the force of the launcher from the spring, and I will need a dimension and the weight and the camera location to input into the drag coefficient equation to find out the trajectory. Here you can see on the right side. Next.
Hello, I'm Charles, and I was looking after the hull. So the hull is comprised of 5 1/8-inch thick aluminum sheets that are welded to an aluminum sheet on top. This was designed by last year's team for accessibility of electronics, which explains the box shape of it. So, stress analysis was performed using the max depth, which was 16 feet or 5 meters, and leads to a pressure of 48,000 pascals. And a factor of safety of 1.1 was found, which definitely needed improvements as the hull cannot fail. And the thing you'll know is that max stress was found at the corners on the top sheet, so all adjustments were made with this in mind. So I performed 3 adjustments. One was increasing thickness to 3/16 inch, and this led to a factor safety of 1.3. The second one was extending the top sheet, which can be seen by the bottom left image, which increased the factor of safety to 1.9. And another one was adding 1.5 inch chamfers to all corners. This increased factor safety to 2.2, but this is tested without the extended top sheet. And with both the extended and the chamfers, a factor safety of 3.1 was found. And another thing to know is that the max stress moved from the corners to underneath the shaft mirror in the bottom right image. And one thing to know is that I noticed no interferences with the assembly. And in terms of weight, all these 3 adjustments added less than a pound.
This is Brian Seger again, and I was working with the hull as well and trying to develop the cover and seal, a plan for that. So current plan was to use a gasket shape identical to the top surface and seal with clamps as shown in the upper right and middle right picture with a gasket in the middle left. This analysis of effectiveness I was not able to perform and still needs to be done. The alternate methods I explored was designing a cover that inserts to the cavity of the hull and making a seal inside the perimeter, but will require a pressure release inside the hull to equate for the displaced air. If you think of sort of like a food container or a pantry storage container with the inner wall as the seal. Another idea was to create a grooved perimeter with a fitted track for an O-ring as the seal. But the reliability and replaceability concerns of the O-ring have been a major concern for that method. Lastly, an example found on the RoboSub RoboNation website was a sub that had used a screwing mechanism as a clamp to attach the cover over a gasket. With this technique, we will need to find a torque value to find the needed force to create the seal. And this idea is predicted to have a longer durability than clamps, as screws don't really deteriorate and there's no bending of metal involved with, or tension involved with the clamps. Next. Also involved was trying to finalize how the electrical housing is going to fit and interface with the body of the hull. Currently, the plan is to attach a rail in each corner with a track to slide the separate electrical board in and out of for use and replacement as needed, and arranging a permanent plug interface in the rear of the hull and connecting the subsystems affixed to the AUV to that. An alternate method that is being explored or was explored was drilling additional holes in the floor of the hull to create additional tracks for mounting additional hardware, electrical hardware. What was discovered is this possibly using those holes in conjunction to mount the frame onto the hull. Also a more modular installation possibility of electrical boards and not having a single giant board. However, more places to seal could affect the stress analysis and factor of safety in the future. It needs to be analyzed. So currently, I was in charge of trying to produce the hull, and with the materials that we were given last year, or that last year had acquired, and but based on our new stress analysis that was performed, that we don't think that these materials were sufficient. So what needs to be done still is finalize the sealing method of the hull with the cover, finalize electrical board interface, obtain these new materials, and then find a full build welding shop or process to ensure waterproofing. As this is probably not a student task, you will have to find a shop that will do that for you. Next.
The second main mechanical design of Lanturn is the frame, and I will be talking about that. Angel. The frame was designed to consist of multiple slots to facilitate the mounting of numerous components, such as the actuator systems, handles, mounting points to join the hull and frame, and more. The main body of the frame will hold the weight of the hull at its top, the 8 thrusters and their housings on its 4 corners, and other systems or brackets on the side T-slots and its undercarriage. The design of the legs on the frame was optimized to carry the weight of the sub from last year's design. The material of the legs was chosen to be 6061 aluminum, and the design would reduce the weight of the leg by 1.64 pounds. However, the design is too complex to manufacture, and the material cost was found to be unnecessary. Moreover, the weight is of no concern since the buoyancy of Lanturn is a problem yet to be resolved. For that reason, the CAD rendering, as you may see, was changed to a much simpler design. The main frame body can be divided into 2 sections, the undercarriage and the top section. The top section is composed of aluminum bars of a 1/4 inch thickness, while the undercarriage consists of slots that are an 1/8 inch thick. The top section has a greater thickness since the weight of the hull will lie on it. The material for the bars and slots were purchased and cut to the dimensions needed, as shown in the bottom right picture. To complete the assembly, standoffs and screws are needed for purchase. A few changes were made or added to the CAD of the frame. The previous design had 2 slots joined together by brackets for the simplicity of CAD assembly. This was replaced with a single T-slot of the same full length. This allowed for new handle mounting points at the center of the T-slot, and the handles replaced the handles that were on the hull for greater stability, which can be seen on the pictures on the right and the handles on the picture below. Previously, the T-slots on the sides of the frame had no mounts to the slots and bars of the frame. This meant there was not a way that the T-slots would join to the frame. In order to solve this, a bracket will be welded to the undercarriage slot and top bars. A set of screws will then join the bracket to the T-slot. The design of the previous year's teams on how to mount the frame and hull was also kept. This design includes welding a bracket to the hull and T-slot and joining both through a latch, as you can see.
Now to begin with the electrical portion, mainly the power distribution board. This section was worked on by Daniel Romero and myself, Jose Barrera. A bit about the reason for having a power distribution board is that prior to these designs, buck converters were meant to be used. A buck converter is used to drop the voltage to any required amount. If this was still the case, then there would be a need of 3 total buck converters, 1 for each of the required voltage, then being 5 volt, 7 volt, and 9 volts from the initial 14.8 volt battery. And the buck converters aren't small individually, therefore they'll take up a lot of space. Last year's team also worked on a design for the power distribution board to not use multiple buck converters. This year we tried to improve on that design by going over their work and seeing what we could change. Some things we noticed were that the chip used was the FD-S5680. There are 3 Arduino headers, 6 servo headers, no drill holes for mounting, and because the chosen components were selected as surface mounted, they all seem to be clustered in the board. This made the overall design of the board big. The dimensions were 97.79 millimeters height and 128.27 millimeters length.
My name is Daniel, and I'll be going over the device operation requirements. The power distribution board is crucial to the operation of the RoboSub, where its purpose is to transfer or distribute the power supply to the various components. Different components require different voltages, currents, and consume different amounts of power, as seen on the table. With an input voltage of 14.8 volts from a single LiPo battery, the correct values must be distributed to prevent any damage to the components and system. Next slide. I will now go over the simulations performed prior to designing the circuit board. To power the different components, an integrated chip called LT3976 was used as a buck converter. The function of the LT3976 IC is to step down the input voltage to the different required values. The chip was selected to help minimize space on the board, and it is ideal for low current circuit designs, with a max output current of 5 amps and an input voltage range of 4.3 volts to 40 volts, meeting the device operation requirements. Using LT Spice, the circuit was designed to conduct simulations. Changing the load resistance outputted the correct values needed. These are transient analysis simulations. This type of simulation just means the analysis of the properties of variables changing over time. Once steady state is detected, the simulation stops as it stays in the same value past that time mark. The top image is the different step-down voltage values, while the bottom image is the corresponding output current values. Next slide. The top image shows the corresponding power consumption, all meeting the device operation requirements. Not only was transient analysis conducted, but efficiency reports were also gathered on LT Spice. These efficiency reports show how well the integrated chip performs the voltage regulation, which results in the proper output values. These values align with the efficiency range on the datasheet of the LT3976, giving us more confidence in the chip's performance moving forward.
I'll now talk about the 2021 power distribution board that we've created. In this design, we planned on improving the overall look, which is why it doesn't resemble the previous team's board. There are now mounting holes on each corner that are 5.84 millimeters in diameter. The height of the board has been reduced to 87.87 millimeters in height and a length of 76.33 millimeters. The battery, as seen from one of the top above headers, has the larger tracer length and width of 5.84 millimeters, of 2 millimeters, my bad, each, on the bottom and top side. That is to prevent them from burning out from the battery's input current that will be passing through. The headers were placed around the board. To evenly spaced in order to not interfere when they are in the sub with any of the other components. We've made a list of the components and the cost for what will be on the board. As seen, needed components would be capacitors, resistors, an inductor diode, the LT3976, the XT90 adapter for the battery, and middle pin headers. All these values were recorded and found through one website called Mauser Electronics, and it is totaling to $82.37.
I will continue here and talk about some of the simulations that we did, starting with Simulink. Simulink is a graphical coding language which allows for simulation and modeling of dynamic systems, and it has the capability to connect to ROS, which is the operating system that Lanturn's computer system runs on. Simulink can also connect to Gazebo for co-simulation. My teammate will give more details on Gazebo's capabilities shortly. The image on the right is a view of the Simulink model of Lanturn, codenamed SimuSub. The purpose of creating SimuSub was that it provided the opportunity to tune PID controllers, which are the basis of the control system. It also allows the team to create and test different control systems. Simulink has tools for state system architecture as well, which the mission planning team uses to navigate and complete tasks. In short, it should work well in collaboration with the work of the computer sciences, mission planning, navigation, and control system teams. The work that had been done so far is to create a model with dimensions, mass, and inertial properties, as well as thruster location. This data was found using the mass property tools in SOLIDWORKS 3D model. Also completed is an algorithm which combines the PID outputs into force and moments on the model. There are two control systems which have been designed as well. The first control system is named the traveling system. Because of its design, it should handle long distance translation and path following well. Let's take a look at the image on the right. The coordinate system represents the Earth reference frame, which you can think of like the arena. The sub moves around inside this reference frame. Lanturn has its own coordinate system as well, which it takes with it wherever it goes. This is called the body reference frame. Imagine sitting inside the AUV looking out the camera window. The orange arrow represents forward for Lanturn. There are 2 points. Point B is a point that the submarine has been commanded to go. Point A, where the cute little picture of Lanturn is our current location. The line D is the position vector from where you are to where you want to be. The line R is that position vector projected onto the horizontal plane. This control system works by rotating Lanturn until its forward-facing vector is parallel to this projected vector. PIDs work by taking the error, which is the difference between the command input and the current location, and working to make that value 0. Once the error is 0, the command location has been reached. For this control system, R is the horizontal error, theta is the yaw error, and H is the elevation error. Here is an output of the simulated traveling system. SimuSub has been commanded to go to the location 530 in XYZ. The top graph represents velocity, with yellow as X, blue as Y, and red as Z. The middle graph is the position, the same color scheme. The bottom graph represents the Euler angles, or rotation of the sub, where red represents the yaw angle. Notice that the velocities are jumping between positive and negative. This means that the sub is overshooting its command and reversing, which is typical of PID controllers that have not been properly tuned. That can also be seen in the position graph in the middle. It can be seen here that the sub is bouncing around the command location. There's still much work to be done in this control system to get it fully functioning, which is work for the next year's team. Let's move on to the next control system. For tasks that require more precision, mission planning should switch to our next control system. The system does not yaw, but rather strafes to the command location, as seen here. Notice that the forward-facing angle has not been changed. The PID uses X error, Y error, and elevation error. The idea is that the traveling system would get the sub close enough to the task until the precision system would take over and move the sub into place. Here is an output of the simulated precision system. The graphs are the same, with the top representing velocity, the middle is the position, and the bottom are the angles. In this example, the sub has been commanded to 30, 25, 20 in X, Y, Z Earth reference frame. Notice that all the angles in the bottom chart are 0. The system is not supposed to have any rotation, so that is a positive result. All of the position lines reach their command locations rather quickly and with very little, if any, overshoot. This represents a well-tuned PID controller and that the control system is fully functional. Further testing needs to be done to determine if the system is robust enough for deployment or if any input or situations would cause issues. For SimuSub to be fully functional, more work needs to be done than has been done yet. Next year's team will be provided guides and other reference material for them to understand the system well enough to continue the work. Some items that need to be addressed are listed here, including fixing the traveling control system, further testing the precision system, simplifying the combination algorithm by making it a combination matrix, integrating decision-making from the mission planning and navigation teams, integration of state machine architecture, and potentially co-simulating with ROS and/or Gazebo. But what they will inherit is a potentially powerful tool for testing, simulating, and tuning PIDs and collaboration with the computer science team.
All right, hi. My name is Eddie Hernandez. I'm an electrical engineer, and for this senior design project, I focus solely in Gazebo simulation, which I'll explain in the next slide. So for this project, I really focus in the robot operating system because I found this to be very beneficial to our AUV team. Simply because it has a variety of tools that allows for a flexible design, such as testing data, communication, perception, data logging. And for this particular semester, I focus on the simulation more. And the great thing about ROS, it has thousands of packages, tools that give our AUV a variety of choices that can include such as sensors, cameras, IMUs, and so forth. Next slide. So as you can see, but more particularly, I've been using Gazebo. That's a software that contains within the robot operating system. This is something that can help our team kind of see our version of our robot model into Gazebo and test out its programming, coding, and something that we can test out before releasing our final design, RoboSub, into the competition. So if there's anything that needs fixing, we can, like say, in the XYZ coordinates, it's not going fast enough, or the sensors aren't detecting obstacles in front of it, we can always change its coding until we fix it, and before implementing into the RoboSub. So this is one of the software that one of our senior design team didn't use, the Gazebo, but for this semester I decided how useful this might be, and I thought I'd bring it and use Gazebo for this senior design. So I really want what I did and tried to do is really I wanted to replicate the arena to match its dimensions like length, width, and height. Something I wanted to use in the Gazebo is at the water environment. Something so that way our team can kind of test its simulation and see how it functions within the water, and add such as like sensors and cameras, something that we'll be also applying in the design, but for next senior designs team. So particularly, I wanted to use the you can see here it shows the robot going into a direction and using the laser scan. Although for this project, for this simulation, it won't be using that particular laser scan. It's just one of the variety of tools that Gazebo has. It can also match the sensors that we have in our electrical components. It doesn't have to be necessarily a laser scan. That can always be changed. So, this is as you can see, it's a really good, useful tool because it tells us how far the presentation, how far the simulation can go. So I did apply and added a camera into the Gazebo simulation, although it's not the water environment that you see here, but this is again a very useful software because we can also see the robot model work in an autonomous environment and kind of see what's in front of it. But for here, I would but it would have been ideal here to have the actual obstacle courses and have the robot model maneuver itself within the simulation. And again, this is something that's very handy for our next senior design.
Hello, my name is Carlin. I am a mechanical engineering student. I'm going to talk about the possible issue of the Lanturn AUV overheating. SolidWorks flow simulation helped greatly in exploring this issue. So, revisiting internal thermals. One of CSULA's previous AUVs, Eagle 2, would overheat and subsequently malfunction. So the question is, what about our current AUV Lanturn? A hand calculation followed by a flow simulation in SolidWorks was done to investigate this last semester. Assumptions were a water temperature of 28 degrees Celsius and a max battery operating temperature of 65 degrees. This is the most heat sensitive object inside Lanturn. From the expected electrical components that would be housed inside Lanturn, a worst case value of 100 watts of internal heat generation was found. Both hand calculation and simulation indicated that there would be no overheating issue, but just barely. However, there were some risks and limitations in this approach. One is the possibility of a future senior design team adding additional components to their RoboSub, such as more powerful processing components for improved computer vision. Also, this previous simulation was done only for finding the steady state condition, and the time to reach this condition was unknown. Lastly, the approach used previously used a very simplified model of RoboSub, and this limits accuracy to some extent. I decided to revisit this issue. I again attempted a SolidWorks flow simulation, this time using realistic internals, as in a more comprehensive CAD model of RoboSub with many of its components in place inside its hull. However, I ran into issues. There were many errors with even getting the simulation to run, and even if it did run, the calculation time was excessive. So to resolve these issues, I had to do a few things. Once again, I went back to the simplified model, but to compensate for this, I increased the heat generation from 100 watts previously to 125, and I ran a transient analysis for 1 hour of real-time operation. So the results of this, it took between 37 to 43 minutes for the parts inside the simplified model representing the battery to reach the max operating temperature of the battery of 65 degrees. And this is fine because historically, the RoboNation RoboSub competitions typically run for a max of 20 minutes, which is 1200 seconds. So we're fine. This means there is a power budget available if a future team wants to, say, increase their computer vision processing ability. They could definitely add more additional processors or a graphics card in the future. And here are some images to illustrate this aspect of this project. First, image 1 on the left shows the simplified model used in both the steady state simulation and the transient simulation. Some components are identified with their heat generation rate, and the boundary conditions of the 28 degrees Celsius water is also shown. The graph on the right shows rising temperatures of some internal components during transient analysis, as well as the average air temperature over time. Note the time it takes for the top shelf and blocks to reach 65 degrees Celsius, which is well over 20 minutes or 1,200 seconds. Lastly, this image shows what the more complete picture of our AUV lantern would look like. There's a lot of components, and in terms of flow simulation, it is very awkward to work with. I ran into many errors, and again, extensive simulation time, even if I could successfully bypass those errors. So I just decided it was not worth using this. So to wrap this presentation up, for a quick summary, on the mechanical side of this project, designing of our actuators has been completed. However, manufacturing is incomplete and there's still testing to be done. On the electrical side, the power distribution board design and simulation has been completed, although manufacturing is still incomplete. On the simulation side of things, much more work is needed to be fully functional, and we are preparing to pass the baton to next year's senior design team. We will be providing them with onboarding material for next year's team to help them get up to speed and be successful.
Well, thank you everyone for watching our presentation. If you have any questions, we will be attending the expo on May 6th at 2:30 p.m. I'll see you there.